All right, CNT125, Chapter 11. Before we talk about things like UPSs, it's always worthwhile to kind of have oriented our brain some basics of our electricity, AC, DC electricity. So they remind us right here, dealing with things like power surges and all can cause some serious frustrating problems. So it's worthwhile to arm yourself with some understanding of electric circuits and electrical components that manage electricity. Absolutely. So let's do a quick detour on some of these concepts we should hopefully remember from science class over the years, if you will. First thing, like charges repel each other. Negative will repel negative, positive will repel positive. Unlike charges attract each other. Okay, that's the beginnings of some of our concepts of electricity flow. We should also hopefully remember, maybe you did this, you hook a battery to a coil of wire wrapped around a nail. When I hook that up, you actually have electricity flow through here. When you do that, that electricity flow creates a magnetic field. In this case, it creates an electromagnet, but I at least get a magnetic field around here. That's important, because the opposite concept is also true. If I move a magnetic field through a coil of wire, it actually produces electricity. If I move a magnetic field through a coil of wire, it produces electricity. Those two concepts are kind of like equal but opposite, if you will. Electricity through a coil of wire produces a magnetic field. Magnetic field through a coil of wire produces electrical flow. Okay? So, hold that in your brain. DC, hopefully you remember, is direct current. Electrons flow at a steady rate in only one direction, negative to positive, like a battery. So as I hook a battery up, electricity is going to flow around here, light the light bulb, and back to here. And what you basically have is the negative electrons are repelling the negative electrons and zooming them around here, and they're being attracted to the positive side of the battery. Okay, just as kind of an example. Meanwhile, AC, alternating current, your electrons flow in one direction for a short period of time, stop, turn around, and then flow in the opposite direction for a little bit, then stop and turn around, and so forth. That's the kind of power that you get from your power company or things like a generator. That's what you're getting from there. AC is what comes out of your wall outlets, alternating current. So when I plug that in, I literally have electrons going through the light bulb and back and back and back, and that lights up the light bulb. Okay. Now, for producing AC, what you literally have is if I have a magnet here on a little rod that I can spin it, as I move that magnet around, this magnetic field moves by this coil of wire, it's actually going to start grabbing these electrons and throwing them through the wire and producing electricity flow this way. As that magnetic field gets away from the coil of wire, it's going to stop grabbing electrons and throwing them. The electron flow is going to stop. As the other pole of the magnet comes around, it's going to grab electrons in the wire. Here's the magnetic field coming by the coil of wire. It's going to grab electrons in the wire, and since it's the opposite pole, it's going to throw your electrons in the opposite direction. So now we're going to get current flow going the other way. That is literally how AC, alternating current, is produced. Your magnet comes by the coil of wire. As one pole comes by, it grabs electrons, throws it one way. As the other pole comes around, it grabs electrons and throws electrons in the opposite way. That's all that is happening when you're producing electricity, AC electricity. And this is a more detailed example showing you just that. In this case, I have the coil of wire moving inside the magnets. Okay. Over here I had the magnet moving inside of coils of wire. I just flipped it around. I have the coil moving inside the magnets. The same thing is going to occur. Like I said, these phenomena are kind of like opposite each other, but they work. So if I look at a hydroelectric plant, I literally have a kind of like a slide of water comes down and actually spins the turbine. Turbine is just a fancy name for fan blade. Spins the turbine, and that turbine is going to grab a coil of wire and spin it inside a bunch of magnets. When you do that, you're going to produce AC electricity. Okay. The same thing would be true for a wind generator. Same idea. The wind is going to spin the fan blade. It's going to spin the coil of wire inside the magnets. And the same thing would be true for either a nuclear power plant or even a coal coal-fired power plant. I have a nuclear reaction, heating a big, actually it's over here, here's your nuclear reaction over here, heating a big puddle of, or big bucket of water. Steam coming off there spins the turbine. The coil wire inside the magnet starts making electricity. And the same thing can be said for a coal electric plant. A big old coal fire heats a big pool of water, makes steam. Steam spins the turbine. Turbine spins a coil of wire instead of a bunch of magnets. That's how AC is produced. Fun side note, Thomas Edison was a huge proponent of DC electricity. He thought that was the way things needed to go and get done. Nikola Tesla was a big proponent of AC. Nikola Tesla tends to be the person that people do not hear of or know about. He was the proponent of AC electricity. So really we can thank him for the electricity that comes out of our wall outlets every day. Here's a picture of Niagara Falls I took when I was up there with our Girl Scouts a number of years ago. While I was there, I had to go visit the Nikola Tesla monument at Niagara Falls. Yes, I'm a nerd. There's me standing with the monument at Niagara Falls. And the reason it's there is because in 1895, Tesla built the first hydroelectric plant at Niagara Falls to generate electricity. Water moving over these big old fan blades, turbines. Turbines spin a coil of wire inside magnets, produces AC electricity. All right, while we're talking ACD concepts, you run into the terms voltage, current, and resistance a lot. Voltage is your electrical pressure. Current is the actual rate of electron flow, and resistance is the reduction of electron flow. So real quickly, a battery is going to produce a small amount of electrical pressure. You're only going to push a handful of electrons, so therefore you're only going to get a little bit of current flow. Meanwhile, your wall outlet is going to have a large pressure up behind it, pushing a lot of electrons, going to have a lot of electron flow. And we measure this in volts. A battery might have 1 or 2 or 10 volts or 12 volts. Meanwhile, your wall outlet is going to have 120 volts. Over in Europe, it's going to have 230 volts. A lot more electrical pressure. Your current flow is the rate of electrons. You almost think of this as like water moving in a stream or a river. If I put a little meter out there and measure how much water is moving by, that is your flow of water, how many gallons per minute. Well, in electricity, we actually do that in electrons per minute, if you will. And that is your amperes or amps. A typical battery might only have milliamps of current. We're talking millionths of an amp. Meanwhile, a typical wall outlet can produce up to 15 amps. And to give you an idea, something like a hairdryer might use 5 amps of electricity while it's running. Meanwhile, a box fan that you have in the window in the summer might only be using an amp or an amp and a half of electricity while it's running. So that's the flow of electricity. Last but not least is a resistance, the reduction of electron flow. Reduction is the kind of the trying to reduce the amount of electrons that are flowing through a circuit, and this can be caused by the material itself, whether it be a wire or the device itself, like the light bulb, the thing at the end of the wire. The typical result of this is actually heat. Why something, a sweeper cord or power drill cord gets hot is resistance of the wire. So things like a hairdryer using 5 amps of current might offer 24 ohms of resistance. Meanwhile, a box fan using 1.5 amp of current flow running might offer resistance of 80 ohms, just to give you some kind of ballpark idea there. So here's the relationship between the three, and there is a relationship between all three. Voltage is trying to push the electrons. Electrons are moving, that's your amperes, and you have something called resistance trying to reduce that flow. And that can be caused by devices and or things like the wire itself. That's your relationship between the three. And again, another side note, if you work with AC or DC electricity, you run into Ohm's or Ohm's law, named after George Ohm. He came up with a mathematical relationship between those three. Current flow equals voltage divided by resistance. Resistance equals voltage divided by current. And your voltage equals current times resistance. That's what that little triangle there is supposed to be for. Some other terms you run into: power converters, changing the form of electrical energy in some way. Inverters, rectifiers, transformers, and regulators. Your inverter is designed to turn DC to AC. As you notice here, I have a little cigarette lighter plugging into my DC outlet in my car or truck. It's going to rectify that in some manner. It's going to change it in some manner to give me AC electricity out. That's your inverter. Your rectifier is going to take AC and turn it into DC. That's this guy right here, a little power cord plugging into my laptop. The power supply in my computer is plugged to 110 volts outside, and I have all kinds of DC power coming out these ports here for hard drives and other things. Yeah, I know it's an old power supply, but you get the idea. Transformer is this guy. No, not really. I couldn't resist. Transformer is this guy. You're either going to see him mounted on the pole up here, or maybe sitting in the front yard of somebody's house. This is if you have wiring on telephone poles above the street. You have these if you have underground wiring. Your transformer is either going to step up the voltage or step down the voltage. Typically, when you see these, you have some really high voltages up here, you know, hundreds to thousands of volts. This transformer is designed to bring it down to a voltage level usable for your house, like 110 or 220 volts. Meanwhile, on the pole, there might be 1,000 volts up there. And your regulator is this guy right here. This is designed to be a regulator that, you know, as electricity comes in your house, it might say 110 volts, but it's not all that regulated. It might be 115 down to 90, you know, 98, 100 kind of volts. It's going to fluctuate up and down. So the regulator is there to try to smooth that out, get rid of the spikes and get rid of the sags to try to give you nice clean power coming to your device. So that leads us to some of our power flaws: surge, noise, brownout, blackout. Surges are the momentary increase in voltage, lightning strikes, solar flares, electrical problems, and things like a surge protector are designed to stop that and get rid of it, or something like this guy here that actually has a battery in is designed to get rid of that surge and not have that harm something. Noise is fluctuation in voltage levels caused by things like EMI or other network interference. Things like this, again, are designed to filter that out. Sometimes you actually have that on the back of these UPS units too. There's actually filtering options. It's gonna level this out and try to get rid of some of that noise for you. Brownout is a momentary decrease in voltage, also known as a sag. And again, your battery units, UPS units, if you have a short one, they're there to kind of fill in that voltage for you so things do not power down or shut off. And then blackout is a complete power loss. Again, your UPS units are there to provide power long enough that other sources like generators can be brought online and bring power back to the facility for, you know, to keep things functioning. But your UPS units are there to provide power, usually long enough that things like generators can be brought online. And that brings us to UPSs. UPSs are basically a battery-operated power source, and they're there to handle these minor fluctuations. They have standby and online. Standby is going to provide power when power goes out. So it's basically there just kind of hanging out. When it notices there's no more power coming from the outlet, it goes click and switches on and provides power from the battery that it has in it. There's a micro time frame that it's going to switch over and kick in. And it does that when it senses no power coming from the wall outlet. Meanwhile, your online UPS, your power coming in from the wall is continually charging the battery, and the battery is pretty much continually providing power to whatever's connected to it. Almost like your laptop, if you will. The laptop battery is always powering the laptop. When you plug it in, you're basically charging the battery. When you unplug it, you're no longer charging the battery. That's the concept of your online. And your online UPSs are usually the better unit because it's providing nice clean power all the time, and the only problem is when the power goes out, it's no longer charging it. So it's like, okay, I'll provide power until we can plug it back in and start charging again. That brings us to when you do with UPSs, they actually have a rating of volt amperes that talks about how much power is needed. And there's actually a calculation here to show you 1.4 volt amp equals basically 1 watt of power. And you might need to do some calculations on that to know how much of UPS you need to provide power to something. And I actually have a link here to a utility that would help you do that. Actually figure out how much UPS you would need to supply power. There's a link there to do it if you want to give it a try.